Now, next I want to move on to our non-spontaneous electrochemical reactions. And when we use them, we call them electrolytic cells. So an electrolytic cell is simply a non-spontaneous chemical reaction that we force to occur in a process called electrolysis. Now, many important substances such as aluminum metal, chlorine gas, these are all produced commercially by electrolysis. In fact, does anybody know what is atop the, what the hell is the name of that thing? It's the big I can't even say that word now. I think it's called the Washington Monument. It's that big spiky thing. Okay. Does anybody know what's at the top of that thing? What caps that thing off? It's a metal. So it has a metal cap at the top. And the reason they used that metal cap, it was the most expensive metal known to man at that time. So we were basically showing off the wealth of the United States by capping it with aluminum. So it's just a big chunk of aluminum at the top of the Washington Monument. And now what's kind of funny about that is that just a couple of years after they did that, a new process, a new electrochemical process through electrolysis was developed to make aluminum. So the price of aluminum went to greater than the price of gold by a few times to down to a few cents a pound. So went from the most expensive metal to the cheapest metal overnight. And again, that was due to a new process called electrolysis. So here's one purpose of electrolysis is, remember I said we want to use these hydrogen fuel cells to produce electricity. Well, one way we could do that is through the electrolysis of water. Basically, you have a battery, or it could be a solar panel, okay? And electricity is passed through a solution. Again, you can see that we've separated it, just using two test tubes in this case. We've separated it into an anode and a cathode reaction. And basically what it does is it takes the water and it separates it into oxygen and hydrogen, okay? We can see that here. So at the anode, we have the oxidation reaction. So that is the water being converted into oxygen and hydrogen ions or protons, and it releases 4 electrons. Okay, now notice that we're forcing the electrons through this thing this time, okay? Because this is a non-spontaneous reaction. The electrons actually would want to flow this way if they were spontaneous, right? They would want to flow from the cathode to the anode because it's a non-spontaneous reaction. So what we do is we put a battery here, some type of power supply, and force the electrons to flow from the anode to the cathode. So this time we're forcing the electrons to flow through this system, okay? So then the electrons come through, and at the cathode, the water again picks up the electrons from the anode and forms hydrogen gas and leaves behind the hydroxide. So you can see that the 4 hydrogen ions react with the 4 hydroxides, so they just become 4 water molecules. They cancel the 4 water molecules over here. So all you're left with is the 2 water going to 1 mole of oxygen and 2 mole of hydrogen, the overall reaction that we see here. So which one of these do you think is the anode and the cathode? Is this first one the anode or the cathode? How could you tell, since they're not labeled in any way? Look at the chemical reaction. And then look at the 2 test tubes. I'm producing 1 mole of oxygen and 2 moles of hydrogen. In other words, twice the volume of hydrogen than that of oxygen. So since this is where the hydrogen is being produced, that must be the cathode. And since this is half the volume, must be where the oxygen is being produced, and that must be the anode. Okay. Okay. Now, also, to produce chlorine gas is really important because we go through a lot of chlorine gas. Remember, most of our wastewater treatment centers take water from natural water sources. So they can have a lot of biological stuff in them, right? Because animals are always defecating and urinating all over the place, and that eventually gets washed into our freshwater systems. Well, that and other things like decaying animals, all of that generates really bad things for us. Okay, so a lot of parasites, a lot of bacteria that would be bad for us, E. coli, all of those things. So we wouldn't want to just drink that water. Okay, you're taking a chance. It might be good, it may not. So to make sure that it's good, we do one of three things to it. We either expose it to a very high-powered UV light, which kills all the biologicals. We bubble ozone through it. Ozone, again, will kill anything biological. Or we bubble chlorine gas through it, which, again, will kill anything that's biological. So a lot of places choose to use chlorine gas over the other options for whatever reasons, usually cost. And this is one way that we can produce not only chlorine gas, but sodium metal. Now, sodium metal is really important in organic chemistry for the reduction of different species. So sodium is used a lot, again, in the production of different chemicals. So one way to do this is to use what's called a Downs cell. Okay, basically what they do is they take sodium chloride, just regular salt, and they heat it up over 800 degrees Celsius until it becomes a liquid. So this blue stuff in here is liquid sodium chloride. It's molten sodium chloride or liquid sodium chloride. Okay, then we have our anode. The anode is just graphite. Okay, and that's our positive electrode. And then we have our cathode, which is just an iron ring that sits around the graphite anode, I'm sorry, okay? Then we force electrons, of course, through the cathode. Chemical reaction occurs, and chlorine gas is then produced at the anode, okay? So it's going from Cl minus to Cl2, okay? So we're producing chlorine gas, and then there's like a hood around the cathode which collects the chlorine gas. Then the sodium metal is being formed around this ring, and then there's just another, like it's an upside down pan inside the molten sodium chloride. Now the sodium is much, much less dense than the molten sodium chloride, so it floats to the top, and then basically gravity just allows it to flow over into some holding tank. And then it solidifies because sodium is, of course, a solid at room temperature. So this is one way that we could produce many metals, such as lithium, magnesium, calcium. And again, this is the only way we can produce them because you couldn't put them in water because these things react readily with water. Okay, so this is how they have to produce these different types of metals, again, such as your group 1A and most of your group 2A metals in pure form are produced through this electrolysis process through a molten chloride salt. Okay, now I will say that this is not the most common way to produce chlorine gas. Usually they just use an aqueous solution of sodium chloride, and the products are going to be chlorine gas, but the other product is going to be sodium hydroxide. Because again, the sodium will immediately react with the water to produce sodium hydroxide. So that is the more common way to produce chlorine gas. But if you need the pure sodium metal, you're going to have to use a Downs cell. Then we have electroplating. So electroplating or electrode deposition is, again, a very important process. So for example, here we have a faucet, and again, the faucet is generally made out of steel, Well, we all know what happens to steel when it comes into contact with air and water. It rusts. So we can't have our faucets rusting on us within a couple of weeks, so we need to protect them. The way that's done is actually a two-step process. They simply take the faucet and they dip it in a solution of copper 2 sulfate, just like we've seen before. Well, what that does is that coats the entire iron in copper. Then they take that copper-coated faucet and now they're going to do electrolysis, a non-spontaneous reaction. They're going to dip it into a solution of chromium-3. That's going to cause the copper to react with the chromium-3 and produce chromium metal. So it's going to completely coat then the iron with chromium. Now, if you've ever worn off or seen a faucet begin to wear off, you'll notice that it has like an orangish layer underneath. Well, that's some of the leftover copper. And then if it's really worn, you're going to wear through that copper layer, it then exposes the metal, and then all of a sudden your faucet begins to rust wherever that is all worn off. Okay, so again, electroplating is a really important application of electrolysis. Another really important electrolysis type application is electrofining of metals. So electrorefining simply means we're going to take a substance. So in this case, I'm talking about copper. So we have a copper, but it's not pure. It has other metals in it. Okay, so this just comes from the manufacturing process of taking copper ore, which of course isn't pure copper. So when it becomes pure copper, it's not pure copper, it has other metals in it. We want to purify it. So for example, when you use copper wire in your house wiring, the impurities in it cause the wire to heat up. It causes resistance within the wire. So the house wiring that you have is relatively pure copper. And the way they do that is through this electrorefining. They take the impure copper and then just another copper electrode. This is going to be our clean or pure copper over here. And this is the dirty or unrefined copper over here. And so basically we have our impure copper will be our anode and our pure copper will be our cathode. We're going to, again, force a reaction to occur. We're forcing the electrons to go from our anode to our cathode, but this time we're forcing them to do that. We simply put it in the solution of copper 2 sulfate. The copper ions are going to travel over, and because of what we set the voltage at, okay, we're going to force the electrons through, and they're going to pick up the electrons, and the copper then will deposit. Now remember, the copper has a positive reduction potential. For that reason, any metals within the impure copper are not going to deposit because they all have a negative reduction potential. Okay? So since they have a negative reduction potential, they just stay in to the solution. Okay? They just remain in the solution. Now, other metals such as gold and silver, they also have positive reduction potentials just like copper, but we set this, remember, copper has a reduction potential of only 0.34 volts. So we'll set this voltage at just above that, 0.35, 0.4 volts. That means that all of these other ones with positive reduction potentials don't have enough energy to actually be deposited onto the copper, nor to even form ions. So they just simply fall to the bottom. So now they could also collect the solid particles at the bottom, which are actually very expensive, silver, gold, platinum, and then they'll further refine these. So they actually get the precious metals out of the copper and then leave the non-precious metals in solution as ions. Okay, this occurs on a massive, massive scale. So this is just a plant that does this electrorefining of copper. Just to give you an idea of the scale of this thing, that is a person right there. That is a grown man standing right there. These plates are huge. And basically it's just alternating pure and impure plates. Okay? So again, these things are huge. Next, let's talk about the stoichiometry of electrolysis. So again, we would want to know, especially if we're like trying to deposit, let's say we're trying to deposit chromium onto a faucet. Well, we want to put a certain amount of chromium. We don't want to put too much because that's just a waste of money. We don't want to put too little because then it's not going to protect the steel as well. So we need to actually quantify it. We're going to do that by simply using this relationship. So Q is the charge this time, and it's in coulombs. So it's not heat. So that's why I put the subscript E here. So Q is the electrical charge. Again, it's in coulombs. And it is simply the product of the current. So that's going to be in amperes. And 1 ampere is a coulomb second. Okay. And then just over the amount of time that you actually deposit, that you force this current through the system. So that's just our length of time that we do it. Okay. So again, like I said, the current is measured in amperes, and 1 ampere is 1 coulomb per second. Okay. So this again ends up being coulombs per second. This is seconds. And so this gives us the number of coulombs that we transferred. We're going to be able to relate that number of coulombs to the half reaction. We're not interested in, when we talk about electrolysis, we are not interested in the overall reaction. We are only interested in the half reaction because we're forcing one of those half reactions to occur. So I want to know how many grams of oxygen are liberated by the electrolysis of water with a current of 61.8 milliamps after 5 hours. Okay. So here's our overall reaction. It looks like this. We have a cell potential of negative 1.23 volts. We need to look at the half reactions. And in this case, since we're interested in oxygen, all we need to do is look at the half reaction that involves the oxygen. And of course, it's already balanced. Okay. So this is the half reaction. What you would look up, of course, we have oxygen going from -2 to 0. So is that oxidation or reduction? And that's important because you're going to need to look this up in the table of standard reduction potentials. So is this oxidation or reduction? The hydrogen goes from +1 to +1, so nothing happened to it. But it goes from -2 to 0. Did its oxidation number increase or decrease? Well, it increased. So that means this is the oxidation half reaction. So when you look this up in the table, you are looking for the opposite of this. Okay, the opposite of this. And this then is the other half of the reaction. Now this is the hydrogen, right? So this is just 0. So this is actually the reduction potential of this. Even though it's the overall cell potential, because this one's 0, it also ends up being the reduction potential for this. Okay. So the way we're going to do this, we're going to calculate the number of coulombs of electrons that are transferred. We're going to convert that to moles of electrons. That's easy. That's Faraday's constant, right? Then we're going to go from the moles of electrons to the moles of oxygen using the balanced half reaction. And then finally, we're going to go from the moles of oxygen to grams by the way we always do, the molar mass. Okay. So we're going to use the molar mass then to get to the grams of oxygen. So putting all that together, first we're going to calculate the number of coulombs. So we're going to multiply the current times the time, but we got to get them in the right units. So again, we got to get that into amps. So milliamps, we're just going to divide this by 1,000. That gives us our 0.0618 amps. Now our 5 hours have to be in seconds because we know an amp is a coulomb per second. So we got to convert our hours to seconds. So there's 60 minutes in an hour and 60 seconds in a minute. So that's going to give us 1,102.4 coulombs. Okay, now we can take those coulombs, and we're going to do this second step now. We're going to take the coulombs, and we're going to go to moles of electrons by dividing by Faraday's constant. So the coulombs cancel, and that leaves us with moles of electrons. Then to go from moles of electrons to moles of O2, we're going to use that balanced half reaction that relates the 4 moles of electrons going to 1 mole of oxygen. So that's where this molar ratio is coming from, that balanced half reaction. Now all we have is moles of oxygen, so we just multiply it by the molar mass of oxygen, and that gives us 0.0922 grams of oxygen can be produced by running 61.8 milliamps for 5 hours. So we can produce 0.0922 grams of oxygen. Okay. Any questions on that? Okay. Then the last thing I want to talk about here in this chapter is corrosion. And corrosion, again, is just another form of an electrochemical reaction. It's just the oxidative deterioration of metal, which again is an electrochemical reaction. Basically, the iron is converted to iron 2 plus, okay, with the release of 2 electrons. And then oxygen reacts with acid, so it has to be acidic. So when it rains, the rain is acidic because of the carbon dioxide in the atmosphere. And so the oxygen reacts with that acid to release 4 electrons. And so the process then overall looks like this. The iron 2 plus then further reacts with oxygen in the atmosphere to form iron 3. Now the reason iron 3 is important because the iron 3 reacts with the water to produce to produce the iron 3 oxide, which is what we call rust. Okay. So that's just corrosion, is just another electrochemical process that occurs in a whole bunch of different steps. Okay, that is it for this chapter. I will go over a whole bunch of problems. Now, we could also deal with electrolytic cells. Remember, these are the non-spontaneous cells, and we're going to use that for all kinds of reasons. We can turn water into hydrogen and oxygen. We can plate a metal surface with another metal. So for example, your faucet is just steel, but it's coated with chrome to prevent corrosion. Well, that's done through an electrolytic cell. We purify copper using electrolytic cells. So we're again forcing the non-spontaneous reaction to occur. And that is just QE. Now this time QE, this has units of coulombs. Okay, QE has units of coulombs, and that is going to be equal to the current that's flowing through the electrolytic cell. So I is current for a given amount of time. Okay, so the number of coulombs that are used within a oxidation reduction reaction is given by the current. Okay, so this is going to be coulombs per second. So current is coulombs per second. That's what an amp is. So 1 amp equals 1 coulomb per second. Okay, so that's what an amp is. And then this time then has to be given in seconds because that's going to have units of coulombs. And then we already talked about the conversion between volts and joules. We know that 1 volt is equal to 1 joule per coulomb, or we could say that 1 joule is equal to 1 volt coulomb. So whichever one you like. I have a stereo system. It's called JVC. JVC, I don't even remember anymore. But so I generally just memorize this one because it's easier, but this is the form that we normally use it in, but just need to remember one of them. Okay. Okay. So those are all the equations that we're going to need to know for this chapter, and that is all of them. This is number 58. It says a constant current of 1.5 amps is passed through an electrolytic cell containing 0.1 molar solution of cobalt-2 sulfate with a cobalt anode and a platinum cathode until 3.6 grams of cobalt is deposited. How many seconds would it take to deposit the cobalt? So when we're talking about deposition, we generally, and we're talking about amps and all that, well, this must be an electrolytic cell. The only equation we know for electrolytic cell is relating the amount of charge. So this is coulombs, right? The amount of charge, which is simply equal to the current passed through a cell for a given amount of time. So if we're asking how many seconds, we are looking for del T in this equation. We were given the current, right? So this is I, so we were given the current, and we're looking for time, so we must know how many coulombs of electrons were transferred. So to find that out, well, we're going to have to get that from the amount of cobalt that was deposited. Okay. So we're going to find the amount of cobalt that was deposited. So 3.67 grams of cobalt. And we'll divide that by the molar mass of cobalt. So the grams of cobalt cancel. So basically what we're trying to do is we're trying to go from moles of cobalt that were deposited to the charge. So at this point, though, I've got to relate the charge is the moles of electrons, right? So the charge is in coulombs, and that's the charge on the electrons that are transferred. So now I got to go from moles of cobalt to moles of electrons. Any idea how I do that? Well, for these electrolytic cells, it's just the half reactions, because the half reactions contain the electrons. And since we're interested in cobalt, all I'm interested in is cobalt. And since we're going to solid cobalt, that means the cobalt 2 plus must be going to solid cobalt. And so to balance this, I'd have to add 2 electrons here. Now we have the balanced half reaction. Now in these problems, I don't even need to know what the standard reduction potential is. It's irrelevant, because all I need to know is how many electrons compared to how many moles of cobalt. So I can see for every 1 mole of cobalt, that has to be in the denominator so it cancels, there's 2 moles of electrons being transferred. There's 2 moles of electrons being transferred. So my moles of cobalt cancel, and I get moles of electrons. But Q has got to be in coulombs. So that means we're going to have to multiply this by Faraday's constant, right? Since there's 96,500 coulombs in 1 mole of electrons, moles of electrons cancel, and we're going to get the coulombs that we need. Now that we have Q, so this is Q, this was for Q. Now that we have Q, we could rearrange this equation and say that this is Q divided by I. So Q, whoops, we never actually calculated this. Q is 12,018 coulombs. So Q is 12,018 coulombs. I was given to us as 1.5 amps. But we know in 1 amp, there is 1 coulomb per second. So the amps cancel, the coulombs cancel, and I have 1 over a second, so that's seconds. So that's going to be 8,012.5 seconds. It asks for how many seconds, so we'd have to put this in scientific notation. So this is going to be 8.01 times 10 to the 3rd seconds. So that's about 2 hours and 15 minutes approximately.